Hello, everyone. Today we're solving squares of sorted array, LeetCode problem 977. Let's understand the problem statement first. We are given an integer array that is sorted in non-decreasing order. Our task is to return an array of the squares of each number, also sorted in non-decreasing order. Let's look at an example. The input array is -4, -1, 0, 3, and 10. After squaring each number and sorting, the output becomes 0, 1, 9, 16, and 100. There are three important constraints. First, the array is already sorted. Second, it can contain negative numbers. Third, we need the output also sorted. Let's explore how to solve this problem efficiently. Let's walk through an example step by step. Our input array is -4, -1, 0, 3, and 10. Step 1 is to square each element. -4 squared equals 16. -1 squared equals 1. 0 squared equals 0. 3 squared equals 9. And 10 squared equals 100. Step 2. After squaring, we get the array 16, 1, 0, 9, and 100. Notice this array is not sorted anymore. Step 3 is to sort this array. After sorting, we get the final output 0, 1, 9, 16, and 100. This is our answer. Now, let's understand the key insight. Why is this problem tricky? Let's look at the original array, -4, -1, 0, 3, and 10. This array is sorted. After squaring, we get 16, 1, 0, 9, and 100. But now this array is not sorted anymore. The problem happens because negative numbers become positive after squaring. A larger negative number, like -1 squared, gives a smaller positive value of 1. But a smaller negative number, like -10 squared, gives a larger positive value of 100. This is the challenge. The input is sorted, but the output becomes unsorted after squaring. Let's start with the brute force approach. The strategy is simple. Square everything, then sort. Here are the 4 steps. Step 1. Create a new array for results. Step 2. Square each element and store it in the new array. Step 3. Sort the result array. Step 4. Return the sorted array. This approach is simple, but it works. Let's look at the brute force code. We define a function called sorted squares that takes nums as input. First, we create an empty result array. Then we use a for loop to square each element. For each number in nums, we append number times number to the result array. After that, we sort the squared values using result.sort. Finally, we return the result array. Let's see an example. The input is -4, -1, 0, 3, and 10. After squaring, we get 16, 1, 0, 9, and 100. After sorting, we get 0, 1, 9, 16, and 100. This is our final answer. Let's analyze the complexity of the brute force approach. The time complexity is big O of n log n. Here's the breakdown. Squaring all elements takes big O of n time. Sorting the array takes big O of n log n time. The total is big O of n plus big O of n log n, which equals big O of n log n. The space complexity is big O of n because we need a new result array of size n. For example, if n equals 5, we need about 5 times log of 5, which is approximately 12 operations. Now, let's think about why the brute force approach isn't optimal. The problem is we're ignoring the sorted property of the input. The input is already sorted, but we're destroying this order by squaring. Then we're spending big O of n log and time to sort again. Let's make a key observation. The largest squares always come from either end of the array. The smallest negative number, like -10, gives a large square. The largest positive number, like 10, also gives a large square. Meanwhile, middle values like 0 or 1 give small squares. Can we use this pattern to create a better solution? Now, let's explore the optimal approach using 2 pointers. The strategy is to build the result from largest to smallest. Here's the key idea. The largest square is always at either end of the array. We compare absolute values at both ends. We pick the larger one and move that pointer inward. Then we fill the result array from right to left. We use 3 pointers. The left pointer starts at index 0. The right pointer starts at the last index. And the result pointer starts at the last position of the result array. Let's see how this works in action. Let's visualize the 2 pointers approach step by step. Our array is -4, -1, 0, 3, and 10. L points to the left at -4, and R points to the right at 10. Step 1. We compare the absolute value of -4 versus 10. 10 is larger, so we place 100 in the result. R moves left. Step 2. Compare absolute value of -4 versus 3. 4 is larger, so we place 16 in the result. L moves right. Step 3. Compare absolute value of -1 versus 3. 3 is larger, so we place 9 in the result. R moves left. Step 4. Compare absolute value of -1 versus 0. 1 is larger, so we place 1 in the result. L moves right. Step 5. Only 0 is left, so we place it in the result. The final result is 0, 1, 9, 16, 100. Here's the optimal code implementation. We define a function sorted squares that takes nums as input. First, we get the length n. We create a result array of size n initialized with zeros. We set left pointer to 0, right pointer to n-1, and position to n-1. Now we use a while loop that runs while left is less than or equal to right. Inside the loop, we calculate left square as nums at left times nums at left. We calculate right square as nums at right times nums at right. Then we compare. If left square is greater than right square, we place left square at the position in result and increment left by 1. Otherwise, we place right square at the position in result and decrement right by 1. After placing a value, we decrement position by 1. Finally, we return the result array. Now, let's analyze the complexity of the optimal approach. The time complexity is big O of n. We make a single pass through the array with 2 pointers. Each element is visited exactly once, and no sorting is needed. The space complexity is big O of n. We need a new result array of size n, but we don't need any extra space for sorting. For example, if n equals 5, we need exactly 5 operations, 1 per element. This is much better than the brute force approach. Let's compare both approaches. The brute force approach has time complexity big O of n log n and space complexity big O of n. The strategy is to square all elements and then sort. This approach ignores the sorted input property. The optimal 2 pointers approach has time complexity big O of n and space complexity big O of n. The strategy is to build the result from largest to smallest. This approach uses the sorted input property. Here's the key learning. When input has useful properties like being sorted, try to leverage them instead of destroying and rebuilding. This can significantly improve your solution's efficiency. Thank you so much for watching this tutorial. I hope you found this lesson helpful and easy to understand. If you enjoyed this video, please hit the like button. It really helps the channel grow. Don't forget to subscribe to the channel for more beginner-friendly programming tutorials and helpful tips. Feel free to comment your questions or thoughts below. I love hearing from you, and I try to respond to every comment. And don't forget to hit the bell icon so you get notified whenever I upload new videos. See you in the next lesson.